Hello, everybody. Today I'm going to talk about another extremely famous problem in robotics. It's called the SLAM problem. It's simultaneous localization and mapping. In this part, I'm going to discuss the EKF-based SLAM, one of the most basic algorithms. This is going to be the first part of a series of videos. Now I'm going to talk about the known data assignment problem. So the table of contents. First, I'm going to give an introduction and define what the SLAM problem actually is and what it tries to solve. Then I'm just going to discuss a few of the approaches to solve SLAM problems, some of the most important solution algorithms. Then we will get into EKF SLAM and describe the main steps in solving the SLAM problem. And as usual, we're going to showcase the results and test it on a fictitious landmark map. So first, introduction, we're going to define the SLAM problem. So as we just mentioned in previous videos, we solved the global localization problem in known maps. So we were able to utilize the measurement model, a probabilistic measurement model, and a probabilistic measurement model, and a motion model, both to predict and update the robot's path in a known map. So we assume that we have full knowledge of the map with no uncertainty involved. So usually now this is not a valid assumption, and the SLAM tries to estimate the map along with the robot state. So it actually assumes that we have no idea what the map looks like, and it tries to update the robot state and the map together simultaneously. So basically this figure out here might show an idea of what the SLAM would look like. So you can see the triangles here are the blue triangles, the filled ones are the estimated path. That's why right here the blue triangles but without any filling are the true path. You can see that the robot actually utilizes the motion model to predict its next step, which is going to have some uncertainty, and tries to utilize the measurement model with respect to the landmarks to enhance its position. And it's actually going to also use an estimate of the current map to do so. And in the meantime, it's also going to try to correct for the uncertainty in the landmark map as it just, goes on. Now, the SLAM problems have usually two types, generally speaking. We have the online type, which is the one that we are going to discuss here, and the offline type, which might be discussed in later videos. So the online type, we're actually just trying to incrementally use the information at each time step to enhance our estimates of the position and the map. The offline, on the other hand, would receive as its input a full robot trajectory and a full set of measurements, and it just tries to come up with the best robot trajectory and the best map to interpret the robot trajectory and the measurement results. Now, some of the approaches to solve the SLAM problems, we're going to give a taxonomy of solution algorithms. So now we are going to discuss some of the most famous solution algorithms. We have the EKF approach, graph SLAM, sparse information filters, and fast SLAM. Now, the EKF solves the online SLAM problem. The graph SLAM is completely offline. Sparse information filters and fast SLAM, although I do not have that much of the expertise on those yet, but they also tend to be a middle ground between the online and the offline SLAM problems. So they don't usually they might incorporate measurements of different time steps into the current time step rather than just waiting for the whole trajectory to do so. Now, of course, we're going to focus on the EKF SLAM. One of the main drawbacks is that it's only valid for landmark type of maps. So this kind of limits its applicability to, landmarks or simple maps, and it usually cannot handle a large amount of landmarks, especially because, we have the data assignment problem. This makes it quite complicated in highly symmetric maps and might lead to divergence of the filter. So now we're going to describe the EKF SLAM algorithm and just discuss all the details. So the first thing that we usually have to discuss when we talk about EKF-based algorithms is the state vector. So assuming that we have a known number of landmarks n, the state vector will have dimension 3 plus 2n, and is given as follows. It's a column vector. The first three components will correspond to the robot state and are denoted by x superscript r. Then we have landmark 1 coordinates, landmark 2 coordinates, up to landmark n coordinates. So this is 2n, and that's 3, so 3 plus 2n. Now the motion model for the robot state, as usual, is the velocity motion model, and we denote it by f of xr, function of the robot state, u and alpha. The landmarks are actually assumed to be stationary, so usually the update equation is just the identity map, so m1x will have to be equal to m1x plus, of course, some noise. The measurement model is the same simplified range sensor model that we used in the localization videos. So it's just so once a landmark is in the robot sensing range, it can sense the distance and the angle with it to that landmark with certain, of course, noise on the range and the angle. And as mentioned before, this is the case of known data assignments. So we also have the index of the landmark associated with the measurement. We are going to make a few definitions that we are going to use in the EKF SLAM algorithm. So first, we define the matrix fx, which is going to be a 3 by 3 identity, followed by a concatenation of 3 by 2n zeros. The matrix fxg, which is also a function of the index g. G will be an index between 1 and n, the number of landmarks. This will be a 3 by 3 identity here, a block of zeros. Then here we have a 2 by 3 zeros. Then we have a 2 by 2g minus 1 zeros, a 2 by 2 identity, and then a 2 multiplied by, of course, 2n minus g zeros. Now, just for a reminder, this is the measurement model between landmark k and the robot state xr. Now, this right here would be the Euclidean distance. X and y are, of course, the parts of the robot state. Theta is also the angle, and this right here would be contribute the angular position of the landmark with respect to the robot local frame. We are ready to discuss the full EKF SLAM algorithm. First, we predict the robot location only. So this amounts to the idea that we're going to use the velocity motion model to predict the robot location part of the full state vector. That is only the first three components, and leave all the other components unmoved or unchanged. That is because we assume that the landmarks are stationary or static, and they just don't have any dynamics. So this simply amounts to the following math. So xk will be xk minus 1 plus fxt. Fx was defined in the previous slide with the motion model minus the previous state. The same idea would apply here. The Jacobian would be the identity matrix, of course, with dimensions 3 plus 2n multiplied by 3 plus 2n multiplied with this expression here. This amounts to the idea that we just keep the Jacobian matrix, the identity for all the landmarks, and just update it for the robot location section of the state vector. And as usual, we update the covariance matrix using these equations right here. Now, of course, the V would be the Jacobian with respect to the input of the motion model evaluated at the previous state, the previous robot state, and at the current input, this would be the covariance matrix of the input, and this is the transformed covariance matrix from the input space to the state space. Now we're going to repeat the following steps for all observations ZG. Now each measurement is composed of a distance, an angle, and an index that indicates to which landmark we are discussing the measurement for. First, we're going to predict the measurement, compute the covariance matrix of the innovation, and the Kalman gain. Now, in this case, the only difference is that HG would have to accommodate for the idea that we are also going to update the landmark positions based on the current location. So it would also have a component, an additional component that is related to the Jacobian of the measurement model with respect to the landmark location. So in the localization, we only had this component, the Jacobian with respect to the state. Now we concatenate the Jacobian with respect to the landmark position. We evaluate those at the current robot state and at the MSG landmark, so landmark with index SG. We also multiply that by fx of index SG. So this is just to, to give the idea that we're using this expression only for landmark SG because it's the one that we are currently updating or that we currently observed. Now Q would be sigma r squared and sigma phi squared, which is the noise parameters of the measurement model. We're going to use the Kalman update for the mean and the covariance, the usual equations, of course. Now it's actually very noteworthy to know that although HG would, only make an update for the SG landmark, it's actually observing the KG. You can see that this actually would not be the case. So KG will not have the same structure as HG. It will also perform an update for probably all the components in the state vector. Now that's actually quite an interesting observation because it means that we also, once we observe a certain landmark, we're going to update our information of probably the whole map. So to reflect this new information, because we kind of know the relation between different landmarks and between different locations of the robot, and we're actually going to update the whole map using this single measurement to the single landmark. So that's actually quite an interesting property of the EKF SLAM. So now we're going to discuss the results of applying the EKF SLAM algorithm to a fictitious landmark map. So now the figure here would show a simple map that we're going to use. It's made up of 8 landmarks given in black dots, and the robot's nominal path will be given in blue. I'm going to play just this short video that shows how the robot is going to move through the. So you can see that the robot just starts here at 0, 0. That's one of the initialization conditions of the EKF SLAM because it really doesn't matter where we start. We could just set this as the 0 reference. You can see that the robot would have to traverse these landmarks once, then twice because it needs to correct the map and its location. Then a third time, it goes through this and just finishes right up here. So that shows some of the results of the position error estimation. I'm not going to show the path this because they are going to be very messy on one, on one plot. So I'm just going to show the position error using the SLAM and with just using the just the simple odometry update. So the figure here would show that the SLAM position error estimate is actually quite better than the odometry only, because you can see using the odometry the error would grow over time because of the integration errors, of course, and the noise on the commands. So this shows that the SLAM was able to correctly predict the position with quite a good accuracy. Now the same would hold for the angular estimation. We can see that in the first few spots there are places where SLAM was better, places where odometry was better. This is usually just a case of the noise. Now if we zoomed into the final parts where the filter might have probably converged, we could get this, which shows that the SLAM was better for the final parts of the simulation. We could see that the error was at approximately peak about 5 degrees, which shows that the SLAM was able to also predict the angular position of the robot quite better than using the odometry only. Now we're going to show the result of the 2 maps that the SLAM was able to predict versus the true map. We can see that the SLAM was able to recover the true map with a really good accuracy. You can see the black dots are the real map, the blue dots are the SLAM map. You can see that they are really, really close. So our algorithm was able to estimate the map and the correct for the robot position, which is quite a great feature of the SLAM algorithms. Now, finally, some final thoughts. Some of the ideas we could do later, we could just, try different approaches. Of course, the graph SLAM, the sparse information filters, the fast SLAM. Of course, we could relax the known data assignment assumption. This could be a later video. We could try different types of features to accommodate for different types of maps. So we could just, try polygonal maps and maybe try a more like a LiDAR type sensor and they use these to construct the map and predict the robot's location with accuracy. Finally, there's also quite an interesting literature that is coming out more recently, which is the use of random finite sets to tackle SLAM problems. This could come in because we have no idea what the number of measurements could be. We don't have an idea of what the number of landmarks could be, and this could be a useful kind of approach or formulation to tackle these problems. And that's it. As usual, thank you very much for listening. Of course, if you have any ideas, comments, different types of problems you want me to solve, different approaches you want me to follow in my videos, I'm more than happy to engage with you in the comments section. And yes, that's it. Thank you again.